So in our example, we have that researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence at the alpha equals 0.05 level of a difference in the population proportions? So the first thing I'm going to do is define my P1 and P2 hat. And P1 hat is going to be School 1. P2 hat is going to be School 2. So we are trying to look at determine if there's a difference in the population's proportions. So our null hypothesis is going to be that there isn't a difference. So I'm going to write this as P1 minus P2 equals 0. You could also write it as P1 equals P2. My alternative is going to be that P1 minus P2 does not equal 0. So I'm just looking for a difference between the schools. I'm not trying to show that School 1 or School 2 is better than the other. So just looking that there isn't a difference. So we have an X1 of 19 and an N1 of 80, giving us a P1 hat of 19 over 80, which is 0.2375. We then have X2 of 26, N2 of 150, meaning we have a P2 hat of 26 over 150, which is 0.196. Now I'm going to check my conditions. So for random, I need to make sure that both, and they did take both of them as SRSs, so we're good there. For independent, our first sample size, our School 1 sample size has to be 80, has to be less than or equal to 10%. And they did tell us that there's at least 1,500 students at both schools, so we're good for there. And then 150 is also less than or equal to 10% of all students. So it says at least 1,500. So even though 150 times 10 is 1,500, I have at least that, so we're good there. And then last one is normal. So 80 times 0.2375 and 80 times 0.7625 both have to be greater than or equal to 10, which they are. And then 150 times 0.196 and 150 times 0.804. Just realized my P2 hat was incorrect. It's not 0.196. It's 0.1733. So 0.1733 and then 0.8269. Both have to be greater than or equal, 67. Have to be greater than or equal to 10, which they are. So all of my conditions are met, which means I can now go ahead and calculate my test statistic. So when we calculate our test statistic, we actually don't want to use the P1 hat and P2 hat when we do our standard deviation in the denominator, because we want to make sure that we're only gathering from the successes and not the failures. So we're going to calculate something called a pooled proportion. which is going to be x1 plus x2 over n1 plus n2. So for our problem, that's going to be 19 plus 26 over 80 plus 150. And that's going to give us 0.196. So for my z, I'm going to have 0.2375 minus 0.1733 all over the square root of 0.196 times 0.804 over 80 plus 0.196 times 0.804 over 150. So I have to assume like my standard deviation, like that my pooled proportion is for both samples. So at this point, you are allowed to use the 2-prop z-test to calculate your z. You can also plug this exact thing in the calculator. Either method you use, you should get a z-score fairly close to 1.168 or 1.17. So again, at this point, I can then use normal CDF with my lower bound of 1.17, my upper bound of 1E99, mean of 0, standard deviation of 1. And if I do that, I'll get out a p-value that I remember because my alternative hypothesis here is does not equal. I would have to multiply that p-value by 2. Or we can go to 2-prop z-test, plug in my x1, n1, x2, n2, and choose whether or not our alternative hypothesis is a does not equal or greater than or less than, and then I'll get my p-value. So no matter which one we do, we'll get a p-value of 2.427. Now I want to compare this p-value to my alpha. Now I didn't state an alpha, which means I'm going to be using an alpha of 0.05. Oh no, sorry, it does state alpha is 0.05. So I want to compare if 0.2427 is greater than or less than alpha, and it is greater than, which means I fail to reject the null hypothesis, which in the context of our problem means there is not enough evidence to show a difference in proportions between the number of students at the schools who don't eat breakfast. So then the last thing at the bottom of this page is just a summary of the 2 calculator functions we discussed today. A 2-proportion z-test, which if you go to stat and then tests is number 6, and you need to know your x1 and n1, your x2 and n2, and then you choose your alternative hypothesis. And it will give you your z-test statistic. It gives you your p, which is your p-value. It gives you p1 hat, p2 hat, and your proportion for your pooled. If you are doing a confidence interval, you again go to stat and tests, and you use a 2-proportion z interval, which is all the way to the letter b. you need to plug in your X1, your N1, your X2, and your N2, and your confidence level as a decimal. It will return the interval itself along with your P1 hat and P2 hat. Let me know if you have any questions about a difference in proportions, whether or not that's constructing a confidence interval or performing a significance test.